Welcome back to another lecture of Statistics 568, Design and Analysis of Experiments. We've done a lot of factorial design so far, the full factorial, the fractional factorial, but all of them have only had 2 levels for every factor. Now, we're going to do 3 levels for every factor because sometimes you need more than 2 levels to get your job done, your experiment run. So when you're working with more than just 2 factors, that is when you have 3 factors, things are kind of the same, but they also become a lot more complicated. Because of all that nice group theory that we were using before, well, it's more complicated. And now when you want to talk about an interaction, what exactly is the interaction telling us? And what we're going to find out is that every interaction term in a 3 to the k factorial design can actually be decomposed into more terms that are more sub-interaction terms. And beyond that, if our factors are ordinal, that is, if they are ordered like small, medium, and large, then we can use polynomial contrasts, and it leads to a whole nother area of investigation, and we're going to be looking at that right now. And welcome back to another lecture of Statistics 568, Design and Analysis of Experiments. We spent the last couple lectures going through factorial designs for binary factors. They're the most common ones that you will experience in research, but we don't have to stick with just binary factors. We can extend that, what we learned about 2-level factorial designs, up to 3-level, and even beyond that. But for now, we're going to start with a discussion on 3-level factorial designs. So a lot of the same intuition that we built over the last few lectures will apply here, but things will be a little bit more complicated because now every term can take on 3 different levels. That means they each require 2 degrees of freedom, and there's going to be more complexities when it comes to aliasing and fractional designs. But we're going to dig into that and try to make some sense out of it. So let's see what this is all about. All right, well, before we jump into the idea of a 3 to the k factorial design, let's just look quickly at the idea of a 2 to the k design again. So we did this, okay, for the last couple lectures, but again, the 2 to the k design, we have every factor takes levels or takes on, let's say, takes on levels of minus or plus, which could, just be -1 or +1, but effectively they're just 2 different levels. We just need some type of an indicator for the 2 different levels. And for, let's say, A, B, and C, we had that A squared is equal to B squared is equal to C squared is equal to 1. This would be for 3 different binary factors if we had, say, a 2 to the 3 design. And we know this just because if we treat the minus and plus as -1 and +1, well, if we square it, we just get back where we started. We just get a 1. So now, what would happen if we instead consider a 3 to the k design? Well, actually, one more thing I also wanted to mention. One more thing about our 2 to the k design, just for juxtaposition's sake, is that we also have here that every main and interaction effect has 1 degree of freedom. Okay. So yeah, of course, we saw that before, that it has 1 degree of freedom. But now what happens when we change 2 into 3, right? And now things are going to change a little bit. So what we're going to do is we're going to denote the 3 factor levels by 0, 1, and 2. So again, 0, 1, and 2, okay, we're going to treat them eventually as arithmetic mod 3, but for now you can think of them as just symbols corresponding to the 3 factor levels. They could be just purely categorical. We have maybe 0 is some control group, and 1 and 2 are 2 different types of medications or additives. Or it could be something ordinal. It could be like low, medium, and high dose, 0, 1, 2. That's one of the more common places you will see a 3-level factorial design is if you have ordinal factors and you have different dosages that you might want to apply from a low, medium, or high, or even a 0 to a low to a high dose. So there are different places where this would show up in practice. Now, in this case, for our, let's say, 3 to the 3 design, well, what happened? Before we get into all of the complexities of 3-level factors, let's just think for a second about what would a 3 to the 3 design look like? Well, the first thing is the sample size, capital N, is going to be 27 data points, 3 to the 3. Okay. What would happen if we, let's say we have factors A, B, and C again? Well, what happens now if we look at our ANOVA table? What we would find is, well, a couple things. We would get our main effects. So let's just say A, B, and C. And then we would have, let's say, our degrees of freedom. And now we don't have 1 degree of freedom for each of these. Remember, the degrees of freedom is always going to be the number of factor levels minus 1. So in this case, it's 3 minus 1 or 2 degrees of freedom for each. And then we're going to have two-way interactions just like we did last time. A, B, A. I'm going to write A cross B for a reason that will make more sense, in a moment. And B crossed with C. So what happens when you have a two-way interaction with 3-level factors? Well, the degrees of freedom multiply. So the same thing happened for our 2 to the k design, but when all the degrees of freedom are 1, I can multiply 1 by itself as many times as I like. I'm still just going to get 1. However, now when I combine A and B, for example, I don't have 2 degrees of freedom, I have 4, and 4, and 4. And when I look at the 3-way term, A, B, and C, I get 2 times 2 times 2, which is going to get me 8 degrees of freedom. So let's count all these to make sure we got everything we wanted, right? Well, we would have 8 plus another 12, 4, 4, 4, so that's 20, and then we get our 26, which is exactly what we want, because it's the sample size 27 minus 1, always for the global mean or the intercept term or whatever you want. Okay, so we've accounted for all of the degrees of freedom, and the same thought process happened as happened with the full factorial design. If we don't replicate it, we don't have any degrees of freedom left for the residuals. But sometimes we would rather not replicate it so that we can, because these designs will start to grow a lot faster, right? 3 to the k will grow faster than 2 to the k. So you have to account for that already with a 3 to the 3, we're at 27 data points. If we were to double that, replicate it for the sake of the residuals, we'd now be at 54 data points. So it can grow quite fast in this case. That being said, you can still estimate all the main interaction effects, look at the sums of squares, try to estimate if they're big or not. You can use methods like, I'm pretty sure Lentz method works, because Lentz method just applies to estimating parameters, and you're assuming that they're null or they're not, and they're just going to be mean 0, or at least most of them will be mean 0. So I think all of those should still follow. But that's what the table would start to look like. But we are going to have to dig in a little bit deeper to figure out what's going on with these terms. Okay, so where do we go from here? Well, the first thing that I wanted to point out is maybe we could do a little bit of arithmetic, modular arithmetic, that is. So just to make sure we know what modular arithmetic is in case you haven't done that before, right? I can add up two numbers, say, well, yeah, what's the easiest? I'll just add up two numbers. Well, we can say I can add up numbers mod 3, which is what we'll be doing here. So if I have something like 1 plus 1, well, that's just going to be 2 mod 3. But if I have 1 plus 2, that's going to be 3, but 3 mod 3 is just going to go back to 0 again. And similarly, if I have 2 plus 2, that's going to be 4, but mod 3 means I would subtract 3 and I would get to 1 mod 3. So all we're saying is we're going to consider arithmetic on the, it's, I guess, technically a finite field because 3 is prime of 0, 1, and 2, where if I add the numbers together, I get, 0, 1, 2, 0, 1, 2. And if I try to add these numbers together, 0 plus 0 is 0, 1, 2, 1, 2. 1 plus 1 is 2, 1 plus 2 is 0, 1 plus 2 is 0, and 2 plus 2 is 1. So I'd get a table that looks something like that if I were to do all the different possible combinations of summing two terms in my, I guess, finite field here of on 3 elements. There is a point to showing you that. That's going to come up in 1 second, so it's not just complete tangent for no reason. Because what we need to do is we need to try to understand a bit about what it means to have A and B interacting. So here's the idea, right? So A cross B is kind of all interactions between A and B. But what we can do is we can decompose this into 2 orthogonal interaction terms. So what we can do is we can consider 2 different ways that we can have these interacting. It's a little bit strange, but let's try this. So what we can have is, let's consider A plus, actually here, why don't we do a big table? Because I think that might be the best way to do it. Forget about C for a second, because who really cares about C? Let's say we have just a B, A and B. And we're going to eventually have something else here. This is going to be our 3 to the 2 design. So if we're going to do a 3 to the 2 design, well, we know what we need to do. We're going to have 9 elements in our design, or 9 data points in our design, and 9 different treatments. We're going to test every combination of A, B, or just A and B together, which will look something like this. All combinations of A at various levels and B at its various levels. Have to try to, there we go. I think we got this. So then the question is, well, what's the interaction term? Well, there's really 2 different ways that we can combine A and B. We can combine it as A plus B. That's exactly what I did up here in that little table. If I add mod 3, and what we would get is we would get 0, 1, 2. We would get a 1, 2, 0, and a 2, 0, 1. Okay, but there's one other interesting thing. We can also combine them as A plus 2B. And if we combine them as A plus 2B, well, we get a 0 let's see if we can do this in my head. 0, 2, 1. We would get a 1, 0, 2, and we would get a 2, 1, 0. So now you can check this, that for any two columns, so we should still have orthogonality, which means any two columns have each pair of symbols occurring an equal, I'll just write it out, equal number of times. So again, if I look at, for example, b and a plus b, I see 0, 0 occurs once. I see 0, 1 is here. I see, let's see, we should have a 0, 2 and a 1, 1 and a 1, 2 and a 1, 0 and so on. So any two pairs of these, so these are actually 4 orthogonal columns when we treat orthogonality in this symbol definition. Now, if we really wanted to have a multiplicative approach to it, like we did with the factorial, with the 2 to the k designs, right? A 2 to the k design, you can think of every column as just being plus or minus ones, which is great because we can just multiply them together and we have that notion of multiplication that we're comfortable with. In this case, it's a little bit harder. I think you might be able to map these. Well, if you have 3 different elements, you could probably map them to 3 points on the complex disk, in which case multiplication should still work. But I think trying to do modular arithmetic here is probably an easier way to approach this. Anyway, the idea is that this is what our 3 to the 2 design would look like. 9 elements, 4 columns. Each of these columns would have degrees of freedom 2, 2, 2, and 2. Not to be confused with the 2's for the symbols, right? Each of them is going to have 2 degrees of freedom, which is going to get me my 8 in total, which is what I should have. So this is where things become a little bit stranger, because it's like, okay, how do we deal with this? Well, we can actually rewrite our ANOVA table as A, B, and then there's 2 ways to write A, these terms. We'll use A plus B, we'll write as AB, and A plus 2B we'll write as AB squared, and each of these will have 2 degrees of freedom. Now, in 3-level world, we have that A cubed is equal to the identity. This is going to be important when we start doing fractional designs with 3 levels. Before, if we squared A, kind of like I said at the very top of these lecture notes, if I square a 2-level factor, right, I kind of get back to the identity. In a 3-level case, I have to cube it, which then makes us look at both cases of B and B cubed. Here, the cube is kind of saying that I'm actually adding it to itself 3 times, A plus A plus A, but this notation with the exponent is often much more convenient than having a whole bunch of pluses flying around, which is going to be a real headache if we try to do that in practice. And you'll see when we do this a little bit later what I mean. Okay, so there's a couple questions. Well, one, what about, let me see if I can move this without, oh, look at that. Good stuff. We're going to move my little orthogonality comment down here, even though I somehow missed, oh, that is super annoying. Let's try this one more time and try to select the entire thing so that I don't ruin the, there we go. Oh, come on. Let's just get this working. Come on, OneNote, do what I need you to do. Good. All right, I'm moving that down because I want room for another column, because what some of you at home might be wondering is, okay, you put in a plus b and a plus 2b, but what about 2a plus b? Or why is that not here? So let's try 2a plus b. So you might think, well, wait, we could probably add in another column. So that's like the intuition from the columns. But if we count the degrees of freedom at the bottom, we realize that, oh, wait, we just lost all our degrees of freedom. 2 plus 2 plus 2 plus 2, it's 8. That's all the degrees of freedom we have in our 3 to the 2 design. So what does that mean? Well, that means if I try to put another column in, it should coincide with one of the columns that's already there. So let's try to write this and see what happens. Well, in this case, I get a 0, and then I get a 1, and then I get a 2. All right. Then I get a 2, I get a 0, and I get a 1. And lastly, I get a 1, I guess a 2, 0. And then no, the last one is supposed to be 0. 5 is, 2, and then 0. Okay, so let's look at this column. Well, this column goes 0, 1, 2, 2, 0, 1. It doesn't coincide with A. It doesn't coincide with B. Does it coincide with A plus B? Well, not quite, but what I'm going to claim is that it actually coincides with A plus 2B, that these columns are identical. And they're identical because, look, you always have 0 matched with 0, 2 matched with 1, and 1 matched with 2. So we flipped 1 and 2. But the point is that they're always matched up together. You never see a 2, 2. You never see a 0, 1. You never see a 2, 0, right? You always see 1 matched with 2, and you see 0 matched with 0 when you look at these two columns. That means that these columns are no longer orthogonal. They now coincide with each other. They're now, in some sense, they're confounded, but they're not really confounded because the blue column doesn't exist. It just isn't an extra term here. So it's one of the confusing things that you might see when you're looking at designs like this. And it's one of the reasons why what we do is we typically would write AB and AB squared, but this is technically equivalent to, I'll write it on the other side. This column would be technically equivalent to A squared B, and this one would be equivalent to A squared B squared. So what we do in practice is that we insist that the first factor in any interaction has, I'm going to say coefficient, even though it's kind of like an exponent of 1. I say coefficient because technically these 2's and 1's are the coefficients that I'm adding up here. So this is 1, 2, and this would be 2, 1. So that's why I say coefficient. So to make sure that we don't have any ambiguities here, we always enforce that the first guy in any interaction is going to have an exponent or a coefficient of 1. And that will make sure that we have everything for our everything we need for our ANOVA table. Like I said before, when it gets to 3 levels, things start to get a little bit crazier. So there's actually one other neat thing that we might notice if we stare at this table here. So let's switch to green or red. Fun fact, this, my arrow's in the wrong spot. This is equivalent to a Greco-Latin square. I love this. I think it's kind of neat. So if you stare at that, you think to yourself, well, wait, how in the world is that a Greco-Latin square? I'm not seeing it. Well, let's try to figure out what I mean by that. All right, so why would this be equivalent to a Greco-Latin square? Well, consider A and B to be row and columns. Then what we can do is we can consider, well, the same table I did above, which is A plus B. And if I consider, let's say, A taking the values of 0, 1, and 2, and B taking the values of 0, 1, and 2, well, we've already done this, right? What we find is we get, is it Greco or hyper Greco? No, I think this is, what we want. What we get here is we end up with a 0, 1, 2, just like last time. Something that's going to look like, not one like that. But if we consider the other column, which has fallen off the top of the page, the A plus 2B column, 0, 1, 2 for B, 0, 1, 2 for A, well, now we're going to have 0, 2, 1. We're going to have 0, 1, 2. We're going to have 0, 2, 1. And we're going to have 2, 1, 2, 0. Okay, so now what we have are these are both Latin squares. All right, so that's pretty neat. Now that I have my my two Latin squares here, I can actually overlay them on top of each other. And what I notice is that these are actually two orthogonal Latin squares. That is, if I turn this, I guess I can use this one as 0, 1, 2, and then maybe we'll replace the 0s, 1, 2s here with, I see I did alpha, beta, gamma in my written notes. We'll do that. So if we turn this one into alpha, beta, gamma, alpha, or not, we already have the alpha, beta, gamma, gamma on the diagonal, and for 0 here, we'll have an alpha, alpha, and a beta. And then for bringing in, we'll do red because it's more contrasting. We'll go this way. We have, let's say, 0, 2, 1, 1, 0, 2, 2, 1, 0. So once again, we have every combination of alpha, beta, gamma, 0, 1, and 2 will occur one place in this table. So in a sense, we have something that mathematically looks a lot like, well, it is a Greco-Latin square in this case. And we'll find out a little bit later when we do things like fractional factorial designs for 3 to the k designs, that you can actually reconstruct Latin squares and Greco-Latin squares from some of these designs. The difference is how you interpret them. In this case, we're assuming we just have 2 experimental factors, A and B, and the Greco-Latin square bits here actually just correspond to the interaction terms, whereas in the actual Greco-Latin square, you would have blocking row and blocking column and experimental factors, alpha, beta, gamma, 0, 1, 2 inside the square. So conceptually, or practically, I guess I should say, there are differences in how you would think about them, but mathematically, it's kind of the same idea is happening here, which I think is kind of neat, right? Kind of ties all this stuff together. Anyway, so yeah, we have all of those meanderings. Let's go to 3 level, or not 3 levels, everything's 3 levels. Let's go to 3 factors to try to show you what happens when we have a 3-way term. Good times. All right, so three-way interaction A times B times C. So we know that we have 8 degrees of freedom for this one interaction term that we have to figure out what to do with. Well, if we follow the rules that I said before, what we're going to do is consider 4 different 2-degree of freedom interaction terms. We're going to decompose it. So we're going to take this and we're going to decompose it into A, B, C, A, B, C squared, A, B squared, C, A, B squared, C squared. Now, each of these is going to actually, it's basically shorthand. It's shorthand notation for modular arithmetic, which is to say that we have A plus B plus C mod 3. We have A plus B plus 2C mod 3. We have an A plus 2B plus C mod 3, and we have an A plus 2B plus 2C mod 3. And each of these is going to have 2, 2, 2, and 2 degrees of freedom. Right, so interactions in a 3-level design start to get very strange. I mean, if you actually had significance, let's say you imagined you ran a 3 to the 3 design, you have 27 data points. Now, what you end up with in your ANOVA table, actually, why don't I write that out? Because we kind of wrote it out above. In your ANOVA table, you would end up with 26 divided by 2, which is 13 different rows. Each of those would have 2 degrees of freedom and correspond to a main or an interaction effect. But if you had significance, let's say here, for A plus B plus 2C, then the thought is, what in the world does that mean physically, right? It's really hard to interpret some of these interactions. So it's good to know that there is an interaction, but actually being able to sort of tease out what's going on there is not always straightforward. That will change a little bit if we have ordinal factors, because if we have ordinal factors, then we can see how the response grows or shrinks or changes as we move from factor level 0 to 1 to 2. We're not quite there yet, though. Actually, we're about to be there. But before we get there, I did want to just point out, trying to drill home the idea of enforcing that the first exponent has to be, you have to have a 1 in the first exponent or the first coefficient, corresponding to this over here. Let's consider, let's see, how do we want to do this? Let's try A plus 2B plus C. So if we, let's say example, if we had the interaction A plus 2B plus C, well, that's going to take on values of 0, 1, and 2 mod 3. Right? Depending on what my value of A, B, and C are, we know it's going to take on a value of 0, 1, or 2. Well, if I multiply this entire thing by 2, then what do I get? Well, I end up with 2A plus B plus 2C is equal to 0, 2, 1, mod 3. So this is exactly what we did in the table. What we did in the table above. Remember in the table above, when I tried to add in that blue column, I said, this actually coincides with, that is 2A plus B coincides with A plus 2B. because of the way the symbols line up. I've swapped the position of 1 and 2, but otherwise everything is the same. And that's exactly what would happen down here. What I did by multiplying by 2 and getting a 2a out front, I've swapped the position of 1 and 2, but those two interaction terms are equivalent mathematically here. So yeah, I think that's more or less what I wanted to discuss for this section. It's a little confusing, so it takes some time to kind of absorb what's going on here. Yeah, it's always good to know that, yeah, and then good to know that, well, I love counting things. I think it's really good to know that if we have a sample size of 3 to the k, then we have degrees of freedom total, degrees of freedom of 3 to the k minus 1. Each row has 2 DOFs. So there are 3 to the k minus 1 divided by 2 rows in the ANOVA table. That's assuming that you break up all of the interactions into their constituent pieces here. I forgot to mention one thing. What do we call this? Let's put that in red here. We call this decomposition an orthogonal component system. Orthogonal component system. Again, it's not always easy to interpret these interactions, but it's good to know that this is how you decompose all of the terms into individual 2 degree of freedom interactions. That is, you decompose big interactions into specific interactions. In R, it's just going to give you all of the interactions together until you tell it to break them apart. And we're going to look into some R code later, maybe in the next lecture, where we'll look at how to actually deal with 3-level factorial designs and how to tell R in the ANOVA table to take a term and decompose it. And that can be really useful because sometimes you would get a big, there's another thing, this is actually quite important. You could have a 3-way interaction term. It has 8 degrees of freedom. It doesn't look significant. But when you break it into 4 pieces, you find out that one of the 4 pieces is actually significant and the other ones are just junk. So it's one of the reasons why it is also very good to understand this, because you can decompose these big interaction terms to try to find out where there may be actual significance within them. So it is kind of fun to work it all apart like that. Anyway, now we're going to move on to the next section, which is linear and quadratic contrast, because these things are a lot more interesting if you have ordinal factors. Linear and quadratic contrasts. This is when factors are ordinal. For example, A takes on the values of small, medium, and large, for example, or otherwise, low, medium, high, whatever you want to say. So in this case, we know that, well, factor A has 2 degrees of freedom. And remember, more than once in this course, I've said that degrees of freedom are kind of like the currency of statistics. We use one every time we want to estimate something, every time we want to test something. Well, what we can do is we can take factor A and its 2 degrees of freedom and break it into 2 1 degree of freedom polynomial contrasts. Right. What does that mean? What that means is I'm going to take A and I'm going to break it into 2 pieces. Those 2 pieces are going to be A sub L and A sub Q for linear and quadratic. And these are going to have contrasts, which are going to look like 1, 0, or minus 1, 0, 1, root 2. And this one is going to look like, I'll try root 6, 1, minus 2, 1 over root 6. Okay, so what does that mean? Well, what happens, right, is that if we consider factor A, let's say A at low, medium, oh, I changed my small, medium, large. Then what we get is and let's say this is the response Y. Well, what we would get is we'd get some box plots, right? Something that might look like this if we were to plot this out. Well, what these contrasts do is they basically say how linear or how quadratic does this thing look. So the linear one, if we do this in green, is going to look for, well, is it increasing or decreasing in a linear direction? In this case, it says, yeah, it does look like it's increasing, so we might get a strong linear contrast. In contrast, we have the quadratic contrast. How many times can I say contrast? This one takes the value of 1, minus 2, 1. So it looks like a V shape. So what we're looking for is a pattern that would look more like this in our data. We don't see that in my hypothetical box plot, so we would probably get an insignificant quadratic contrast. Whereas, again, in contrast, if I had my SML here, small, medium, large, wonder if that's how they picked the acronym, we end up with something like this. We would have a strong quadratic contrast and a weak linear contrast, because now it looks like it goes down and back up again. Now, it doesn't just have to go down and up. It could be the reverse of that. It could go up and down. And similarly with the linear contrast, it doesn't have to step increase. It could also step decrease. And that's what these contrasts are looking for. And they're actually quite useful, because you can use them then to say, as my dosage of whatever drug I'm administering goes from small to medium to large, I'm seeing a linear growth or drop in my response. Similarly, maybe less frequently, but still very common, you might see this V shape. I mean, it actually could be an upside down V. It could be if I give a small dose, I see a low response. If I give a medium dose, I see a high response. Then if I give a large dose, the response drops because maybe I've overdosed or something like that. So if you're trying to promote growth in plants, it's like you give them a little water, they don't do so well. You give them a decent amount of water, they do well. You give them too much water, they all drown, and that's no good. So you could imagine where you would see a quadratic contrast going from low to high to low, or in the other case, just up, up, and up. So contrasts, again, are really useful, and they're very interesting in this case, because now for your ANOVA table, what you could do, right, is you could take your A, I'm still in red. You can take your A and break it into an AL and a AQ. And you could take your B and you could break it into a BL and a BQ. Of course, that leads to an interesting question. What do we do with the interaction term again? Well, it's a little bit messy. because we could also take our interaction term A crossed with B, the 4 degree. Remember, it has 4 degrees of freedom. And what do you think we're going to do? Well, what we're going to do is we can cross A linear, B linear, A linear, B quadratic, A quadratic, B linear, A quadratic, B quadratic. So we can actually break our all of our ANOVA table up into, and look at this, we actually have 8 of these, so we would each have 1 degree of freedom for all of our polynomial contrasts, and it just so happens they're all orthogonal to each other. You can see that by taking, well, you can see that at least for A linear and A quadratic here by doing a dot product of these two. If I do a dot product of these two, I would get a -1, a 0, and a 1, and then I get some denominator, which doesn't matter because when I add these up, I get 0. So those two things are orthogonal. If we went to higher order contrast, if we had more than 3 levels, we could continue to develop orthogonal polynomial contrasts, which are just going to keep looking like jagged ups and downs. Yes. So, and in that case, yeah, we have all of our 8 degrees of freedom here, which is, once again, we haven't lost any degrees of freedom. We're testing something with every single one of them. Great. So the formula are pretty terrible. I'm going to write them all down and we can stare at them for a second. So as above here, we had the formula for A with linear and quadratic contrasts. Now, if I were to consider, say, I actually have enough, well, I'll just write it on the next line. I have some room here, but if I wanted to consider A linear and B linear, what does that mean? Like, what is that thing? I should say, actually, I forgot, my notation was slightly different. The notation I was using in the lectures was in the lecture notes is AB linear linear. So then we'll do a colon here because we're not actually saying it's equal. What is this contrast? Well, it's an interaction between A and B, and it's saying that the response, the linear contrast in A is linearly changing in B, or equivalently, the linear contrast in B is linearly changing in A. I'm going to draw a picture, but first I'm going to write down the equation. So the equation would look something like this, which is, I want to look at the linear contrast. What I should do is I should write down the big grid of y's. So if we imagine our data points in A and B, we can write them in a grid. We have 9 observations. We have, starting from the bottom left in graphical order, we have, instead of like matrix order, we have y0, 0, we have y0, 1, and we have y0, 2. We have y1, 0, y1, 1, y1, 2, y2, 0, y2, 1, y2, 2. So what we're saying is that if we want a linear contrast in A, we would take, what does this vector up at the top mean? It means that we would take, let's say, y with an index of 2 and subtract y with an index of 0 and look to see the change between the last guy and the first guy. If it's big, then we say there's a linear contrast. If it's not that big, then there's not a linear contrast. In this case, what we're going to do is we're going to have something that looks like y22 minus y20 minus y02 minus y00. So this, and then you can rearrange this, but what we're basically saying is we're looking at y22 minus y20. So we're saying this guy minus this guy, and we're comparing, and then we're subtracting it from this guy minus that guy. And then, yeah, we're sort of taking one and then we're subtracting it from the other. So what does that mean? Well, what that means, an example, going back to my box plots, would be like saying if B, we want B0, A, I'm just going to write 0, 1, 2 for my factor levels. A, 0, 1, 2, and A, 0, 1, 2. And this is going to be B0, B1, B2. So this is an example. There are other ways that you might get a significant linear contrast, but one way you would get a significant linear interaction contrast would be if you saw a linear increase, say, like this. Then you saw something that looked, well, like it wasn't changing. Then you saw something that looked like it was going down. So this interaction is actually quite interesting because what it's saying is that when B is set to level 0, the response increases in A. When B is set to level 2, the response decreases in A. Because there's actually, the middle terms don't actually come into play, this middle one is probably irrelevant because whenever there's a 1, it doesn't actually show up in our equation here. It's just 2s and 0s. So the 1s probably don't really matter, but it's good to just give you an idea that you can have the behavior of the response with respect to one factor changing as another factor changes its levels. Yes. Okay, so that is an example of a linear contrast. Do you want to try a quadratic one? Let's try a quadratic one. All right, so a quadratic contrast or a linear quadratic contrast, we'll say LQ. Well, again, what you're going to do in this case is you're going to do you're doing a linear contrast on the quadratic contrast. So what that looks like is, okay, there's going to be a normalizing coefficient out front, which just so happens to be 1/2√3. You don't have to worry too much about the normalizing coefficient. It's just there so that as a vector, this thing would be, I guess, orthonormal to all the other vectors, which means that it has length 1 in some sense, in magnitude. But that's not as critical. The idea here is that we would do y22 minus 2y12 plus y02. And we're going to subtract from that y02. Make sure I'm getting this right. Nope, I did it it's y20 minus 2y10 plus y00. So what is this? Well, what we have is we have a quadratic contrast. We have a quadratic contrast, and then what we're doing is we're doing a linear contrast of the quadratic contrasts. That is, we're taking one quadratic contrast, another one, and we're subtracting one from the other. And what we're looking for is a linear change in the quadratic contrast. So I think I had my A and B backwards here, but they're both linear, so it doesn't really matter. In this case, we're looking for a quadratic contrast in B that changes linearly in A. And you can sort of reverse this. So let's try A equals 0 and B 0, 1, 2. And then over here, I'm going to skip the middle one because we don't care about A is equal to, yeah, I guess I got my my indices are all kind of messed up, but it doesn't really matter. 0, 1, 2, and this will be A is equal to 2. So a significant linear quadratic contrast might, again, this is just an example, EX for example, it could look like this, where when A is set to 0, we see a strong positive quadratic contrast in B. But when A is set to 2, we see a strong negative quadratic contrast in B. So you'd have something like that. Let's see, do we want to do the other two examples, or is this getting kind of boring? Well, I guess the next thing we'd talk about is a fractional factorial design, and I don't really want to start that for this lecture. So we're going to be boring and do the next two examples of polynomial contrast interactions. We have AB QL for quadratic linear. In this case, what we're going to get is, this one's kind of the same thing, but it just changes. Okay, so this one's kind of the same thing, but you're going to just change the indices in the above one. But there is a different way that you can interpret it. So it's an equivalent interpretation, but I will write it down just so that you can see it. First, I'm just going to change the, because why not? I'll just write it all out. y22 minus 2y21 plus y20. And that's a quadratic contrast, which is then linearly contrasted with another quadratic contrast. Yeah, this is some good stuff. All right. So another way we could think about it in this case is that we could have three settings, A0, B at 0, 1, 2. We can have A1 at 0, 1, and 2. And we can have A2 when B, I have to indicate this as B, is set to levels 0, 1, and 2. So now what we're looking for is we're looking for a quadratic change in the linear contrast. That is, we want to see a quadratic change in the linear contrasts of B. So one way that we might see that is, remember, what's a quadratic change? A quadratic change means we go from one level, then we flip it, we start somewhere, then we go down, then we go back up again, or vice versa. So in this case, we could start with a strong linear contrast in B, when A is set to 0. Something that might look like this. Then when A is set to 1, it might flip and go the other way and start to decrease. But then when we get to 2, A is equal to 2, that is, it might just flip back again. And then we say, oh, well, now we're going the other way again. So this is what a quadratic linear interaction might look like. Now, I do want to point out these are kind of equivalent ideas here. Mathematically, we're just kind of rearranging the terms, and which one are we looking at first or second? Is it the linear quadratic or quadratic linear? Now, we've got one more to do, so let's just write it all out. the last one that we're going to do is going to be the quadratic contrast. And this one is going to be a 1 over 6, root 6 times root 6. And we're going to have a quadratic contrast of quadratic contrasts, which mathematically is going to look something like this. It's pretty terrible, but we're going to write it out anyway. We're going to get this. We're going to have a 2 here for the quadratic of the quadratic. Plus y, 1, 0. And the last term, y, 0, 2, minus 2y, 0, 1, plus y, 0, 0. All right, so what do we have here? Well, we have a quadratic. We have another quadratic contrast. We have a third quadratic contrast. And what are we doing? Well, we're contrasting them quadratically. It's sort of the inception level of a dream within a dream, a quadratic within a quadratic. So you can think of this as being something like a at level 0, a at level 1, and a at level 2, if I got the indices correct. If not, you can equivalently think of it as b at level 0, 1, and 2. It's actually equivalent. You can rearrange the terms and think of it as a contrasting driving b changing quadratically, or b driving a changing quadratically. Anyway, I'm going to draw one more sketch of box plots because we made it this far. We might as well just go all the way. And what we get here is a0. Let's say a is equal to 1. That's way too long of a horizontal axis. And a is equal to 2. And then we have our b at 0, 1, 2, b at 0, 1, 2, and b at 0, 1, and 2. And in this case, we're looking for quadratics to be changing quadratically. So one way that we might see it is to have a V shape at a is equal to 0, a V shape in B at a equal to 0, which then turns into an upside down V for a equal to 1, which then turns into a V once again for a equal to 2. All right. Are you sick of box plots yet? This is an example of a quadratic contrast changing quadratically. It kind of goes from V to upside down V back to V again. Again, when you get to some of these higher order interactions, they're a little bit hard to interpret. But at least in some of these polynomial cases, you can get some idea of what's going on. The idea that one factor, the way one factor affects the response, is affected by another factor. And this can happen certainly in practice, like my hypothetical example of drowning a bunch of plants by giving them too much water. So, yeah, this is a lot. But this is roughly what we're going to do for a 3 to the k design. I do notice that there's still some time left in the class. I don't want to start 3 to the k minus q factorial designs. So why don't we look at some R code and see what's going on? We'll be back in 1 sec to look at that. And now we're back after a brief interlude where I took some time to write up some quick code so that we could analyze some 3 to the k, or in this case, a 3 to the 2 factorial design, not fractional yet. So if you're looking at the screen here, you'll see that I have loaded in, now I have loaded in the Agridat package full of agricultural data sets from about 50 to 70 years ago. Maybe some are more recent. The data set that we're going to look at for our 3 to the k factorial designs is this sugarcane data set, which is the Chinloy fractional factorial data set. Now, we haven't talked about fractional factorial designs for 3-level factors, so we're not going to look at the entire data set yet. In this case, the entire data set is a 3 to the 5 minus 1, which is why they put a 1/3 out front design. But what I'm going to do is just extract 18 observations and only take 2 factors. So remember, every factor here is going to have 3 levels. A full 3 to the 2 factorial design is going to require 9 observations. I'm going to double that and take 18. That way we have extra degrees of freedom for our residuals. So what we're going to do is first just load this data set into DAT for short, and then we're going to use the transform function as noted. Well, actually, why don't we look at this data set first with a head here so we can see what it looks like. So this data set, there's a lot more going on than we're going to discuss in this brief moment right now. But just to look quickly at it, there's a yield. That's the response that we're interested in modeling. Something about the amount of sugarcane produced per plot with given soil treatments. We have a block factor, a row, and a column because this is one giant field, presumably. So you can include those factors as well. And then we have all the experimental factors of interest. There's 5 of them here, N, P, K, B, and F, which are all different things you can add to the soil, like nitrogen or phosphorus. More details are down here. Apparently the data was collected in a, sugarcane plantation in Jamaica in 1949. So, yeah, good times. Anyway, what we have here is this collection of data. There's more information, as I mentioned, but what we're going to do is we're just going to extract factors B and F. So we have a simpler data set to look at. Then we're going to revisit this data set in the next lecture and look at it in its full glory. But what I was trying to get to is the fact that we need to transform. We're going to use the transform function to tell R that all of these experimental factors should be treated as ordinal factors and not as numbers. Because remember, R will default to thinking that 0, 1, and 2 are actually the numbers 0, 1, 2. We don't want that. What we want is it to have 3 factors, and it'll know that 0 is the smallest, 1 is medium, and 2 is large. In this case, 0 typically corresponds to no additive of that type. 1 corresponds to a small additive, a smaller dose, and 2 corresponds to a larger dose. So as you'd imagine, we're very much interested in polynomial contrasts here. We want to know, is the yield increasing as we go from 0 to small to large dose? Is it decreasing? Is it flat? Does it go up and down like a quadratic? These are all questions that we can answer from our data set. So first of all, we have to transform it. So now it knows that these are ordinal factors. Then what I'm going to do is I'm going to use the order function in R to order the rows based on the factor levels. The reason I'm doing that is because I want to extract the first 18 rows, but I have to make sure that I extract all possible combinations of B and F. And if I don't order them, it's not going to be the right data points. So that's all I'm doing in these lines here is saying, get the order, apply the order, and then extract the first 18 rows and columns 1, 9, and 10 to give myself a simplified data set that's going to look like this. So this is my simplified data set. We just have the yield and we have 2 factors. We're ignoring the rest just to, again, get an idea of what a 3 to the 2 design might look like in practice. And here we have it. So we can fit a model to that, right? There's not much more to do. I do want to note that these 2 columns, B and F, are orthogonal in the sense that every pair of symbols will occur an equal number of times. So we should see 0, 0 twice in here. We should see 1, 1 twice in here somewhere, hopefully. Yep, there's 1, 1. Good. All right. And so on, if we went through the whole thing. Now, when I fit the model, we'll know if we were wrong because we'll see that the degrees of freedom won't be right, or there will be something something will be a wrong if our factors are not orthogonal, or at least it won't be as what we would expect to see, depending on how we differed it. So you could have a design where your factors are not orthogonal to each other. You don't have this nice balanced condition. It just is not as efficient as you'd want it to be. So ideally, this would be the way we would set this experiment up. Okay, so given all of that, let's fit a model. So here I'm just saying yield is going to be a function of b times f. And let's see what happens when we look at the ANOVA table. All right, so here's our ANOVA table. We find out that factor b, which is Bagasse, I'm not actually sure what that is. Apparently it was applied pre-plant at various tons per acre. I'm going to have to look this up because I have no idea what it is, and now I'm kind of curious. But side tangent, the important thing to look at here is that we have our two factors b and we have f, which is whatever filter press mud treatment is, which is also applied tons per acre. Now, if we look at our ANOVA table, which is what we're interested in, we see the usual setup, except now we have 2 degrees of freedom for both of our main effects, and we have 4 degrees of freedom for our interaction term, because this b crossed with f is a full interaction. It's all possible interactions between b and f. We haven't split it up like I talked about in the lecture, but we're going to do that in the next line of code. But first, we can just look at all of this. So this is what we get. We also have 9 degrees of freedom left over for the residuals as desired, because I'm imagining this. I'm taking this data set and I'm pretending that it was a 3⁻² design that was replicated twice. Now, in practice, that's not what it is, but we can still sort of use it that way for instructional purposes. If I only took 9 observations, there would be no degrees of freedom left over for the residuals. Actually, I can do that just to, before we go forward, I'll just show you what happens if we do that. If we type in summary, and then I can actually subset my data and say subset 1 to 9. If I only take the first 9 observations, then what I see is I get sums of squares and mean squares for b, f, and the interaction term. But again, no f value and no p value because there's no denominator. There's no residual sum of squares in this case, so I can't get f statistics or p values. Presumably, we could use something like Lentz method, but I'd have to figure out how to split up factors for Lentz method. Actually, it might work. Maybe we can try that at the end of the lecture. But right now, what I do want to do is just highlight what happens in this table. And that's that we see that factor f has some amount of potential significance there. We have a p-value of about 2.5%. So in practice, it's below the magic 5% threshold. I guess it's significant. But if we set our threshold to be 1%, it wouldn't be significant. If we, for example, set 5%, but we used the Bonferroni threshold and said we actually did 3 hypothesis tests, so I should probably divide this by 3. Well, now my threshold is 1.6%, and this is above that. So it seems to be like there could be some significance in f. But maybe if we were to look at the polynomial contrast, we can see even more interesting information. We will. I kind of know where we're going with this, right? But that's the thought process, right? So what you can do is you can run a line like this in R. And here I'm running summary on the model, but I'm saying split. And split is going to require a list of lists. It's kind of like the inception again. Here we have a list of factors here, b and f, and I'm telling it to split on linear L and quadratic Q contrasts. If b, for example, had more factor levels, 4, 5, 6, 7, I could do higher order polynomials here as well. We'll look at this later in the course when we look at, I think, 5-level or 7-level factors. I forget exactly which, but we will look at this again. For now, we only have 2 different polynomials we can fit, linear and quadratic, because we only have 3 observations or 3 levels for every factor. Anyway, I'm going to stop rambling and just hit enter and see what happens. So now our ANOVA table has expanded. If you notice, we still have b
F and BF with their original degrees of freedom and sums of squares. But more interestingly, now the sums of squares and the degrees of freedom are decomposed into a linear and a quadratic piece. So for B here, well, it wasn't significant. It's still not significant when we look at the two contrasts, but we do note that most of the sum of squares related to B is associated with the linear contrast and not the quadratic contrast. Now, similarly, we see the exact same thing happening for F here. F was sort of significant at some level. It had a p-value of 2.5%, which is getting small. But more interestingly is that when we split up by the polynomial contrasts, we see that we have a linear and a quadratic. Now, most of the sum of squares is in the linear contrast, not the quadratic. And just to make sure it's clear, if I add this number and this number, I get the sum of squares for F in total. So I'm really just taking the sum of squares for F and I'm breaking it into two pieces, one linear, one quadratic. It so happens here that the linear piece has most of the variation attributed to F is coming from the linear contrast. And that's good because now that we only have one degree of freedom associated with it, it's actually making our test statistic much larger and our p-value smaller. Now, to be a pedantic statistician, we typically don't want to compare p-values. You wouldn't go here and think to yourself, well, okay, 0.8% is smaller than 2.5%, so it's a more significant result. Because typically in statistics, if we want to do everything properly, we would set a threshold and say, okay, if my p-value is below a threshold, we reject and deem that to be a significant result, regardless of whether it's just a small bit under the threshold or some absurdly tiny 10 to the minus 10 p-value. That being said, I think it's still worth noting that you get a smaller p-value out here because there's a very good chance that you might have a setting where your original factor F, say, may not look that significant, but when you split it up by contrast, you then find out that there's a piece of it that is actually really significant. When it's all aggregated together, you can sometimes miss the significance. So it is worth taking that into account. And then down here, we have our interaction polynomial contrasts. Again, none of them are significant. It is still worth looking at, though, because there is a chance, as I mentioned, that even though the main term is not significant, one of the contrasts may be significant. And it's a way where you can find hidden significant in a term. When you first look at it, you don't see any. And there are different ways to do contrasts also for categorical variables. When you have an ordinal variable, typically what you would want to do is you would do something like this. You would do your polynomial contrasts. But if you had just pure categorical, then polynomial contrasts don't really make sense. On the other hand, you could consider different ways of combining your factor levels into different ways. We'll look at this a bit when we look at 4-level factors in a later section in the course. But regardless, yeah, that's more or less the whole point. Also, I did want to note that here we see very much significance in the linear term. So if I go down here and try to plot the data, or if I try to plot the yield with respect to the factor levels of F, what I'm guessing based on this, okay, I know what the answer is because I already did this, but we'll pretend I don't. What I'm guessing will happen will be that we will see something like those box plots I drew in the lecture. Either we'll see a linear increase as factors go from 0, 1 to 2, or we see a decrease as we go from 0, 1 to 2. So this will tell us whether F, the filter press mud, is improving or hindering the growth of sugarcane. So let's look at that plot and see what happens. Aha, and it's increasing. Excellent. So as you can see here, we have at 0, when there's no filter mud, we have a yield that is lower, and then it starts to go up and up as we add some filtered mud and we add even more filtered mud treatment. So this is what you would expect when you see a significant linear contrast, or again, you might see the reverse, something going down rather than going up. either way, you would still get a significant linear contrast. But here we don't see anything quadratic. Remember, quadratic would look more like a V shape or a wedge shape. So lastly, we can also plot with respect to B. So here, B does not have any significance in either the linear or quadratic. So we'd expect it to look kind of flat, like the box plots are all just kind of sitting next to each other, neither increasing nor decreasing, nor V-shaped nor wedge-shaped. And yeah, that's what we get. So again, they're not perfectly aligned. The median, the black line here, which corresponds to the median, is slightly increasing, but based on the variance and the fact that there's a pretty big spread here in 1 and 2 and etc., there is no significant changes, significant contrast, nor is B just the factor itself significant in our ANOVA table. Right, so that's more or less all I wanted to say about that. We can look, another way we can look at the data is to go back and type in summary.lm, and we can say AO, not AOV, MD. And if we look at the summary.lm, that's going to compute the coefficients for the linear model. And here we kind of get the same result out, specifically that F linear is significant, and it has, I think, just about the same p-value. It probably should have the same p-value, yeah, because mathematically you're actually running the same test there with 1 degree of freedom. It's an F test with 1 degree of freedom is kind of equivalent to a t test, because if you square a t distribution, you can get an F distribution out. Fun little side fact in case you forgot about how F and t distributions work, but regardless, you can get the same results in this table as well, if you want to look at it that way. So these are just the various coefficients that are computed for the linear model. Yeah, actually, we still have, well, we're kind of over time, but there's really no time commitment or time constraints here. So we're going to go off script for a second and see what happens if I apply lengths method, which should be in the BSMD library. And let's see what happens if we do a length plot. I didn't actually plan this, so we'll just see what happens. Cool, so there's length plot. Again, we don't see anything significant using lengths method, but of course what length said was, you probably don't want to use my method if you have the ability to just do an F test. If you've replicated your experiment, it's kind of like, well, why even bother if you can just do the F test itself? So, and here you do see the linear and quadratic contrast. So I forgot that, yeah, it will do it based on the estimated coefficients. Yeah. But we could try just to see what would happen if we apply it to our unreplicated experiment. I suspect we're not going to see any significance at all, just because if we didn't for 18 points, we probably won't for 9 points, but we can try it anyway. Yeah. The values just get smaller. The pseudo standard error gets bigger because we have fewer data points to work with. And yeah, it just gets worse overall. So again, lengths method, quite interesting tool, but at least in this case, we'd miss a lot of significance if we tried to apply it to this data set, when we could rather just apply the, the F test, right? Anyway, going forward, the next thing we're going to talk about is the fractional factorial design when we're looking at a 3 to the k minus q design. And yeah, we're going to get some crazy aliasing going on there. So prepare yourself for that. And when we're done discussing all of that, we'll go back and look at this sugarcane data set in its full glory. And we can look at all 81 measurements and what we can learn about how to get the best yield for your sugarcane crop, assuming you're sugarcane farmer in 1940s Jamaica. But yeah, I'll see you in that lecture.